Greetings to all my tech heads out there in the KevTechify nation, and if you're new here, welcome. In this episode, we're going to look at path determination. We'll be discussing the two functions of a router. We'll go over some router function examples. Then we'll take a look at best path equals longest match. Then we'll see some IPv4 and IPv6 longest match examples. And finally, we'll look at building the routing table. This episode is part of my series on switching, routing, and wireless essentials for the CCNA. I'm Kevin here at KevTechify. Let's get this adventure started. There are two functions of the router. First one is to determine the best path to forward packets. In a network, you're going to have redundancy, and so there's probably multiple ways to get to the final destination. Let's look at an example. Let's say we are traveling from Los Angeles to New York. And for you, the best way to get from Los Angeles to New York may be something like jumping on an airplane at LAX, landing in New York, and that is your best way. It's the fastest way you want to get there. But for me, I enjoy the scenery. I enjoy looking at the different spots along the way. I enjoy the drive. So for me, I'm going to jump in the car. But then I have different choices on the routes. I could go through Texas to Florida and then up the East Coast. I could go up to Colorado, then across the top of the Midwest, all the way over to New York. Different ways to get there, different paths. Now, I may choose the best path based upon maybe I want to stop and see something special. Maybe I want to get some barbecue in Texas. Get some nice brisket in Texas. I'll go through Texas to get to my final destination. Now, does me choosing to drive through Texas versus you taking an airplane, does that make one route better than the other? From each of our points of views, no. We have our preferred method. That's the way we want to do it. The second function of a router is to forward packets towards their destination. A lot of times when a router gets a packet in and it makes that decision to forward that packet on, it's not going to get it to its destination. Maybe it has to go to another router, and then another router, another router. And so that router is going to forward it towards its destination. It's going to get it in the right direction. Now, for me, when I go and drive towards Texas, I'm going to head east from Los Angeles, right? Head east. I'm not going to head south. Typically, I'm not going to head north, but you could, but typically the best route is towards the destination. And so I'm going to head east to get me towards my destination. That's what routers do. Get you toward your destination until you finally reach it. How routers forward these packets, they build what we typically call an IP routing table. It has a list of all the networks this router knows about and how to get there. And when we go to forward these packets on, it looks at that information and sends it out. Here happens to be the routing table for router 1. As we can see here, it's got some information about codes, but then down here on the bottom, this is a list right here of the networks it knows how to get to. Now, this is a small network. It only knows how to get to 3 different networks. If we look at our diagram up here, we only have 3 networks that we can get to. We got 192.168.1, then we got the 192.168.2 network, the 192.168.3 network. All we have is 3 networks. We don't have any internet connection, so we don't have to worry about it at this point in time. Just a nice, small, simple network. And that's all we need to know about in our routing tables. As we said, there's multiple paths to the destination a lot of times in networks. And what we do here is we have to figure out a way to choose that best path to get to the destination. And the routing table here, it contains, for each entry, it contains 2 parts. And it contains what we call the prefix, which is that network address. And then we have the prefix length. That's how long is that network address portion. Now, to get that information to get towards its destination, we have to have a match between the destination IP address. And so we grab that piece out of the packet because there's that destination IP address information in the header of the packet. We grab that information out, we look at our routing tables, we look at those routes we have, and we have to match those up. We go through and match the bits. And you have to at least match what we call the prefix, that network portion. You can match more than that, but you have to at least match that prefix. And the prefix is used to determine what we say the minimum number of far left bits that you must match. If you think about an IPv4 address, we got the network portion, we have the host portion. You must at least match that network portion to be routed. If it doesn't match, if you don't match at least that, it will not get routed. Now, you can match more than that, which means you could have multiple matches in there, and the best path is the longest match. If you have a /16 address where 16 bits are in the network portion, and you have two entries in your routing table, one matches 16 bits, the other one matches 24 bits, the best path is going to be the one that matches the bigger number of bits. It's going to be that /24 because it matches the 16 plus an additional 8. Now, when we talk about prefix, it's a sort of a generic term that applies to IPv4 and IPv6 addresses. It's that network portion. It's that common portion between those addresses that's either given to you by the IPv4 subnet or the IPv6 prefix. And so when we say prefix and we're talking about routing, note it can apply to IPv4 and IPv6. It's that network portion of those addresses. Here's an IPv4 example of the longest match. This is our address here, 172.16.0.10. And remember, the computer, it looks at it in binary, and that's how you have to think about it, is it's going to match up the bits in binary. And when we look at this, we have a routing table, and we have three different entries here. We got entry 1, 2, and 3. This entry, this network portion, is a 172.16.0.0.0/12. And so this is the network portion of this. This is the prefix. Remember that term we talked about as a prefix. The second entry we have is the same address, 172.16.0.0, but it's a /18. That would be matching these first 18 in our prefix. And then the last entry we have is 172.16.0.0, same network entry, but it's a /26. And we would match the first 26 bits of that IP address all the way out to there. Now, because the third entry matches 26 bits, that's the one we're going to use to route our information out of. So route it out an interface towards the final destination. That's the one we're going to use. Now, remember also that it has to be at least the prefix long. So for IPv4, it has to be at least the subnet. This IP address here didn't specify the subnet, but let's say we put in a /24 is the subnet. When we look at our routing entries, this /12 is less than this, so we couldn't even use that because it's smaller than that. You have to be at least the prefix length. The second entry is a /18, which is less than 24. We couldn't even use that one. The only one we could use is the third entry. It's a /26. It's more than that /24. And so we at least match the prefix. So you have to at least match the prefix length to get that routing information, to use that routing entry in the table. Here's an IPv6 example. Same rules apply. We have our address right here. 2001 DB8 C000:99, and then it's a /48. /48. We can look at these entries. Routing entry 1, 20, or 2001 DB8:C0. This is where this network portion, this prefix ends from here. And because only 40 match, it's less than the prefix that's stated up here, we can't use this one. It only has a match of 40 bits. We can't use this because it's less than the prefix from our actual IP version 6 address. Down on routing entry 2, it's a /48. We could use that one. And down here, it's a /64. We could use both of these. /68, it matches here. But then the third entry, we look at 2001 : DB8 : C00 : 55555 : that's the network portion. If we look up here at our address, remember in an IP version 6 address where there's double colons, that represents that there's all zeros in there. So that's : 0000 : 0000. Fill it out to it's 128 bits total. 1, 2, 3. In the fourth spot right here, we have 55555. But when we look at the actual IP version 6 address in the fourth spot, 1, 2, 3. In the four spots right here, we have 000, and we're matching up to 64 bits, which is more than this right here. We can't use this because it doesn't match the 64 bits. These 64 bits don't match. The match has to go all the way up through this fourth grouping of address or fourth grouping of hexadecimal numbers. It doesn't match, so we can't. This is not a match. We cannot use this routing entry. So the only valid one we have here is the second entry. The one 2001 : DB8 : C000 : /48. That's the only one, and that's the longest match. And that's what we have to look for, is the longest match. 1 was below the minimum here. 3 did not match this fourth part between the address and the information in the routing table. 2 matched all 48 bits, and it was at least the prefix given by our address. I hope you're liking this episode on path determination. If you have the time, please leave a comment and let me know what you think about path determination. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. How the router builds the routing table, it goes through a couple steps. First thing is any directly connected networks to that device. And you can think of them as when you go into an interface and you set up an IP address on that interface on the router, that's a directly connected network. You had to do some configuration. That network is directly connected to it. Those entries, those networks get put into the routing table first. After we have the directly connected networks into our routing table, then we add in the remote networks. And how we can add those in are typically two methods. We can either use static routes or we use dynamic routing protocols. Static routes, you manually have to enter in yourself. Dynamic routing protocols, we let the routers have a conversation between them and let them decide which is the best route to do. And then finally, after the directly connected networks and the remote networks, then we look at the default route. And what the default route is if there's no entries that match at all for how to route that traffic, we're going to send it to the default route. Typically, it's another router that will hopefully know how to get to its final destination. And this has a prefix length of 0. And what that means is no bits match whatsoever. No bits match whatsoever. And if we don't know what to do with it, we're going to send it here. And a lot of times this is called the gateway of last resort. I don't know what to do with it, so I'm going to send it here. Hopefully this person knows how to handle it, or this router knows how to handle it. And then of course, hopefully they do. If they don't, they will send it to their default route, their gateway of last resort. We do need to have a little bit of a conversation on the idea of a directly connected network versus a remote network. Here we have a diagram. We have 3 different routers. We have some devices connected on the end of R1 and R3. We've got 6 networks in this example. Down on the bottom left, we have the 192.168.10.0 network. Then we have the 192.168.11.0 network. We have the network between router 1 and router 2 That's network 3. It can't be any of the existing ones, so it needs to be a separate one. Then between R2 and R3, we have network 4. And then on the other end of router 3, we have network 5 and network 6. We have 6 different routers, or sorry, 6 different networks here in our network. And the idea of directly connected and remote networks changes from router to router. If we look at router 1, right here, router 1, network 1 is directly connected. That means it has a connection coming into here. There's going to be an IP address configured here, and it has that physical connection in there. Network 2 is directly connected. Directly connected, it's coming in on gig 001. It has an IP address set up there as the default gateway for this local area network. And network 3 has that connection coming in here. It's on serial 010. It has an IP address set up. So network 3 is also directly connected. We're going to make the assumption here that we're running some sort of routing protocol, either static routes or dynamic routes, that each router knows how to get to all 6 of the networks. The first 3 on R1, they're directly connected, but R1 also knows how to get to R4. R4, we know if we go out S1 here and go this direction, we can get closer to the network. Network 4 isn't directly connected. There is no connection going into R1. There is no IP address set up on R1 for network 4. That makes it a remote network. R1 knows how to get to network 5. Network 5, you go in this direction once again. You go out serial 010 towards R2, and it will get you closer to network 5. And so for R1, network 5 is a remote network. And network 6 is, once again, is not directly connected. There is not a network, there isn't a wire that runs from network 6 directly into R1. So network 6 is a remote network. That would be for R1 here. Those. R2 has its own set of directly connected and remote networks. If we look at R2 here, network 1, which is down here on the bottom left, you have to go through R1. So there's no wire from network 1 that runs directly into R2. We have to go through another router to get there. That's a remote network. Same thing for network 2. We have to go through R1 to get there. There is no wire directly connected into that. That is a remote network. Then we have network 3. Network 3 is this serial connection. This serial connection connects directly into a serial port on R2. It has the interface S010. It has an IP address configured there. Network 3 is directly connected. Network 4, once again, serial connection connected into serial 011. It has an IP address. Wire from network 4 is directly plugged into R2, so that is a directly connected network. Then networks 5 and 6 down here. To get to networks 5 and 6, you have to go through another router. There is no wire from either one of those there's no wire from either one of those networks running into R2. Those are remote networks again. And then over here for R3. For R3, let's mark that was R2. And then for R3, we have our 6 networks. Network 1, 2, 3, network 4, network 5, and network 6. Network 1, we have to go through 2 routers to get there. There is no direct connection to that. It's not, network 1 is not directly connected to R3, so that's a remote network. Same thing with R2 or network 2 over here. You have to go through at least one router to get to R3. So that's a remote network. Network 3, you have to go to at least one router. You have to go through R2 to get there. That's a remote network. Then we have network 4. Network 4 is this wide area connection, this WAN connection. It connects into serial port 010, serial port 011. It'll have an IP address set up here. It's directly connected into R3. So that is a directly connected network. Same thing down here with network 5 and 6. Network 5 and 6, that's the default gateway for those respective LANs. Directly connected. You have a wire running from that network right into R3. So those are directly connected networks. And if we compare this across, looking at all three routers, these networks change. On R1, network 1 was directly connected. On R2, network 1 was a remote network because we had to go through R1 to get there. And if we look at R3, network 1 here is a remote network. We had to go through R2 and then R1 to finally get there. They're not directly connected. As a general rule of thumb, if you have 3 connections coming into your router, you will have at least 3 directly connected networks. Here on R1, we have one line coming in here. We have another line connected into here. We have a third line connected in here. If we look at our chart, we have 3 directly connected networks. Now, the reason I say at least 3, we could set one of these up as a sub interface if we were doing some sort of router on a stick, something like that, and we had a trunk interface, so we'd have multiple IP addresses there, but you should at least have 3 directly connected networks. R2, we have 2 WAN connections coming in, and you should have at least 2 directly connected networks. If we look at our little table here, we can see that we have 2 directly connected networks. On R3, we have 3 wires coming in. We have 3 connections into R3, and we have 3 directly connected networks. It was my pleasure to provide you with this wonderful episode on path determination. If you like this episode and you got value out of it, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All my socials and contact information are on my website, KevTechify.com. There you can find out how to get all these episodes in video and podcast form. In the upper right is my playlist for my series on switching, routing, and wireless essentials for the CCNA. Thank you so much for watching this episode on my series on switching, routing, and wireless essentials for the CCNA. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.